Hey guys, today we're going to be solving this problem which basically asks us to determine how the equilibrium position will shift. Okay, so they give us this reaction here and we see that everything is a gas, so we can consider all of them. So at first it asks how it'll shift if you add H2. So you're adding more of a product, which means you have less of HI, which means in order to reach equilibrium, you must shift left in order to compensate for the added hydrogen. So this will be a shift left. Next, we have if we remove a product, which is I2, right? I2 is removed. You're taking away a product, which means like that. You're taking from it. You're taking from it, not completely. Which means that we're going to have to go this way because that means that there's going to be more on this side, as we see. So this shift right here is going to have to be a right shift. Next, we have if we remove some of the HI. So we're taking away some of our reactant, which means we're going to have more product, which then means this is going to have to be a shift left, because what we're basically trying to do here is we're trying to compensate for this loss. Like, let's say we have, like, I'm trying to, like, create the best analogy here, but, like, a molecule, and, like, this is a reactant, let's just say, and this is a product, but they have to be, like, this ratio, and I'm taking from some of this. That means I'm going to have to move this way and add some here in order to compensate. Okay, now they're telling you in a rigid container, they're adding argon gas. So for this reaction in a rigid container, they're adding argon gas. Well, argon is not part of this reaction, so you want to actually know what happens? Nothing. Argon is not part of this reaction. The partial and initial pressures are, and the concentrations are unchanged. Okay, E tells us the volume of the container is doubled. Doubled means by 2, right? But there are equal numbers of product and reactant gas molecules, so a change in volume will not have an effect, meaning that for every 2 HI, there is 1 H2 and 1 I2, which means that the ratio is the same. Technically, from products to reactants, it's a 2-to-2 ratio, meaning if you double this times 2, this will double times 2, and you'll become a 4-to-4, and eventually, let's say 8-to-8, 16-to-16, etc. So nothing happens here, and this is not always like a circumstance. Now I have this formula down here written because it's telling you the temperature decreases, so it's exothermic. It's an exothermic reaction. What it's telling us is that it's exothermic as in heat is a product, right? So your delta H here is going to be a negative value. So if your temperature is going down, you're obviously going to have less heat, right? Your heat is going to go down, which means that you technically have less product if you're seeing the correlation. So if you're removing some of your product, it's just like you're removing I2 or you're removing H2. Your equilibrium position is going to shift right because it has to compensate for the lost heat. So these sometimes are a little confusing to people, but you have to it becomes really easy once you just understand that with temperature decreasing, I look at it like this. So we have W plus X goes to WX, and then we have W plus X goes to WX. So we have heat here, and we have heat here. This is an endothermic, but this right here is an exothermic with a delta H equal to a negative value and a delta H equal to a positive value. So if I'm dropping my temperature for an endothermic reaction, my temperature goes down. I'm going to obviously shift this way because I'm losing some of this. Let's say I lost the H. I'm going to have to take from here to get my H back. And if my temperature goes up, I'm going to actually shift the inverse because that means I'm gaining. So now I don't have H, I have 2H, let's just say, for reference. So that's it.